Hello and welcome to week 3, lecture 3. We're going to talk about uniform circular motion and also relative motion. This comes from chapter 4, 4-5 and 4-6. So it's going to be uniform circular motion, sample problem 4-5, and then relative motion. So as the moon orbits the Earth exerts a force on it. The force is always directed toward the center of the Earth, no matter where in its orbit the moon is. We see this in the figure. Any position the moon is in, the force points to the center of the circle in the center of the Earth. And a force that always, so let me be specific here. So the force always points towards the center of the Earth, but what ends up happening is that the force is pointing towards the center of the circle being the circular orbit of the moon around the Earth. And so a force that always points toward the center of a circle is called the centripetal force, which means center seeking. So that's what this is in this case. And there's no other forces acting here, so the acceleration must also point toward the center of the circle. This is referred to as centripetal acceleration. But if there's acceleration, doesn't that mean that the velocity must be changing? Velocity is a vector, so it changes either in magnitude or direction or both. In the case of uniform circular motion, like the moon orbiting around the Earth, the velocity changes direction, but the magnitude is constant. And you can see that here, our velocity vectors are present. They're the same magnitude, but they're obviously pointing in different directions depending on where the moon is around the Earth. And another thing to note about uniform circular motion, which is shown in this diagram, is that the total velocity is always tangential to the circle. So if you're trying to figure out the direction of the velocity at any point, just keep that in mind. So if we have the moon here, the velocity would be pointing up over here, tangential. Or if the moon was in this position, it would point down over here. Click too soon. Okay, now let's look at the relationship between some of these variables. We start with a particle moving in a circle in circular motion, and we have two snapshots of the particle at two different positions, so P1 and P2. And we have the velocity vector at each point. And the magnitude of these velocity vectors is the same, but their direction is different. To move from position 1 to position 2, the particle travels a distance of 2 times r times theta, which is the arc length here, 2r theta. Let me say it does that in a time interval, well, what we use as time interval. And so from that, we can get an equation for the velocity going from 1 to 2, and that's 2r theta divided by the time interval. We can also see that the x and y components of the velocity at these 2 points are given by, just like with projectile motion, just breaking it up based on the angle. So the velocity in the x direction is, both of them are v cosine of theta. That makes sense. They're both pointing in the same direction. In the y direction, it's either positive or negative v sine of theta, and that also makes sense because they're pointing in opposite directions. And we can use this information to find the average acceleration in each direction. So unsurprisingly, since the x velocity was the same in both positions, the average x acceleration is 0. But the average y acceleration is given by this negative v squared over r times sine theta over theta. And we can take the limit of this equation as theta approaches 0. So that would be decreasing these theta until they reach this position P, which is like the positive y axis. And if we take that limit, we find an average velocity or the average y acceleration of negative v squared over r. But this point here, like this p and also either of these, they're arbitrary. We could take points anywhere around the circle and we would end up with the same relationship between velocity, acceleration, and the radius. And this is the centripetal acceleration. So it's given by v squared over r, and it points toward the center of the circle. So that's why there's not a negative sign. For this specific example, there is a negative sign, but say if it was over here on the circle, it wouldn't be negative. Or if it was over here, it wouldn't be negative. But yeah, so that is the centripetal acceleration. And if there's an acceleration, there must also be a net force pointing toward the center. And we can plug in the equation for centripetal acceleration into the force equation. And we see that the force is mv squared over r. And I also just wanted to include an additional note. There is this relationship between velocity, period, and radius. So 2 pi r is just the circumference of the whole circle, and the period is the time it takes to travel that full circle. So from that information, we also have an equation for the velocity. Now for an example problem. The moon revolves about the Earth, making a complete revolution in 27.3 days. Assume that the orbit is circular and has a radius of 238,000 miles. What is the magnitude of the gravitational force exerted on the moon by the Earth? Okay. So we're gonna write down what we're given, but we need to do some conversions. So the period is 27.3 days. We do not do physics in days. So we're going to convert. So there's 24 hours in a day. And there are 60 minutes in an hour and 60 seconds in a minute. And this gives us the period of 2.36 times 10 to the 6 seconds. And then we're also given the radius, but that's in miles. We don't do physics in miles. So let's convert. There are 1,609.34 meters in a mile. So this gives us a radius of 3.83 times 10 to the 8 meters. And then the other thing we need to know, since we're asked for the gravitational force, is we need the mass. And I'll just let you know what that is. It's 7.36 times 10 to the 22 kilograms. So force in the centripetal force is given by mv squared over r, but we don't know v. But I just told you the equation for it, right? The circumference of the circle, so 2 pi r divided by the period. And we happen to have all of the necessary information. So 2 pi r is 3.83 times 10 to the 8 meters. And the period is 2.36 times 10 to the 6 seconds. And this gives us a velocity, I'm rounding here, but it's 1,020 meters per second for velocity. So now we can plug that into our force equation. So we have our mass, which is 7.36 times 10 to the 22 kilograms. And then we have 1,020 meters per second squared divided by the radius of 3.83 times 10 to the 8 meters. And this gives us a force, and I'm rounding again, of 2 times 10 to the 20 newtons. So very big force, but these are very big objects, so not unreasonable. Okay, so we're going to jump back to talk about relative motion real quick. Okay, so let's consider the motion of a particle as described by two observers in uniform motion relative to each other. So remember the car, bike, and the person on the sidewalk? Think of it as maybe someone in the car and someone on the bike, but neither is accelerating. They're moving at constant velocity. There we go. So what we have here, we have one, well, we'll start here. We have one reference frame, one observer, given by S as their frame of reference, and each observer has their own coordinate system. So reference frame S has this coordinate system. Reference frame S prime has this coordinate system. And both of them are getting information about the position of this particle P. So let's see, vector here, S, the vector R subscript S prime S is the position of the origin of the S prime coordinate system from the S frame. Okay, it's going to sound a little weird, but just take those slow. But the first subscript is whatever we're looking at. So, for example, both of these are the positions of the particle or the object that we're looking at, and that P is first. And then the second letter is whatever reference frame is looking at it. So that's where we have S prime, so it's the origin, the position of the origin of S prime in the S reference frame. And then, so that's what these are here, then is the position of the particle from in the S reference frame and the position in the S prime reference frame. Just making sure I'm not missing something. So we know vector addition now, and we can say that R prime S, or R, sorry, mixing it up already for you, that R S prime S, this, plus R P S prime equals this vector here. So we end up with this vector relationship between them, where the position of the particle relative to the S frame equals the position of the particle, or the position of the S prime frame relative to the S frame, and plus the position of the particle relative to the S prime frame. We can also take the derivative with respect to time and get velocity in the same way. So that would be if the particle is moving with a certain velocity relative to each frame. And again, it's just the velocity of the particle relative to frame S equals the velocity of the particle relative to frame S prime plus the velocity of frame S prime relative to frame S. And because the reference frames themselves aren't accelerating, because that was one of the rules, is they can't be accelerating relative to each other, the acceleration measured in either frame for the particle is the same. So that's what these are. The acceleration of the particle from the S frame equals the acceleration of the particle in the S prime frame. So the main idea here is, if you want to know how fast the object is moving in one frame, you need to know how fast it's moving in the other frame and how fast the frames are moving relative to each other. Okay, and your application assignment has some practice on this, so you will get some time to work through it. That's everything. Have a great day.